Hi everyone, we're going to talk about ROC curve today. ROC stands for Receiver Operating Characteristic. It's a pretty old terminology. It's a little hard to understand just by looking at the name, so we will go through step by step to see exactly how the curve is constructed. ROC curve is really constructed from a series of confusion matrices. In order to understand ROC, you first have to understand what a confusion matrix is. The confusion matrix is a very convenient way to summarize the performance of a classifier. You do not construct a confusion matrix for a regression model. So a regression model that predicts values does not produce confusion matrix. You can only do this for classifiers. That classifies the target variable into zeros and ones, yes or no's, and so on and so forth. So here you will see the actual y value is called the gold standard or the condition or the labels, right? So whatever you call it, the target or the truth or the actual y variables is these two columns over here. Okay, so we have the positive and the negative, or ones and zeros, ones and negative ones, yeses or nos. This is our prediction. So these are the y hats, the test outcomes. The test outcome can also be positive and negative. Okay, so this is the actual answer, the correct answers. These are the predictions. So if the correct answer is positive and you predict positive, then it's a true positive. If the correct answer is positive, but you predict a negative, then you have produced type 2 error or a false negative. If the correct answer is negative, but you predict a positive, that means you've conducted a false positive or type 1 error. If the correct answer is negative and you predict negative, then you have correctly made a good prediction that is a true negative. Okay, so you can see the red areas are the mistakes. So we can calculate the error rate, or we can also calculate how correct we are. So sensitivity is a way to calculate how correct we are in terms of true positives. Specificity is to calculate how good we are in terms of the true negative. So we're trying to figure out how good we are. Okay, so sensitivity is true positive divided by all the positives. Specificity is looking at the true negatives out of all the negative answers. Okay, so these are both measures of good performance. What we want to do is, well, this is just another summary of how good the model is. So sensitive is a good thing. It measures how good you are in identifying true positives. Specificity is also a good thing. It's a measure of how good you are at identifying the negatives. Okay. However, when we're constructing an ROC curve, we are really trying to figure out the ratio between the good performance versus the bad performance. So let's look at an example. So if you think about classification with a regression model, the regression model will usually produce a list of probabilities. So these are probability values in the prediction. So using X as an input variable and Y as a target variable, we build a prediction model, a classification model, and then using that classification model, we can generate a list of probabilities for each of the data points. And then using these probabilities, we can convert them into class decisions, yeses or nos. That conversion will depend on the threshold that you pick. Okay, so usually in this course, we've seen a lot of using 0.5 as the threshold. However, you can actually use a range of possible values. So we're going to start with the smallest value we can have, which is 0.15 in this particular case. That would divide the probabilities into two classes. So those those that are less than 0.05, and those that are greater than 0.05. Okay, we only have one that's less than 0.05, so anything less than the threshold gets classified as a no. Anything that's above the threshold gets classified as yeses. Okay, so these are our predictions, or the y-hat classes. Okay, now we can compare the prediction to the actual answer, which is the actual y's, and we can see that this is a correct prediction, the first one, but the second, this whole bunch over here are all misclassified, right? So the correct answer is no, but they were all classified as yeses. So these are all, this is a bunch of misclassifications. These are correct, right? So the yeses that were correctly predicted as yeses. So we can summarize this performance. Trying to figure out how to get an eraser. I don't think I know how to do that. So anyway, so we have the y. Yes, sometimes it's 1 versus -1. This is in support vector machine. We have 1 versus -1. In logist regression, we oftentimes have yeses and nos. So it doesn't really matter. You have two classes, and you have two classes over here in your prediction. And then we can count the number of true positives, which is 1, 2, 3, 4 over here. And then we don't have any false negatives. We have 5 false positives over here, and then we have 1 true negative. So with these numbers, we can calculate the sensitivity, which is a good thing. So that's how good we are in terms of identifying the true positives. We are 100% accurate. Specificity is a measure of how good we are identifying true negatives. We're not very good at that. Only 1 out of 6, so that's a 17%. Performance in terms of good performance. So what we want to do is we want to take 1 minus specificity, which tells us how bad we are. So this is a bad rate. Okay, bad performance. This is good performance. So we're at identifying true positive at 100% accuracy, but we also commit a lot of errors on the false positive. So this is the false positive rate. Okay. So the ROC curve is basically a ratio between true positive rate, which is sensitivity, and false positive rate, which is 1 minus specificity. So this is your good performance. This is your bad performance. So what we want to do is we want to plot my good performance against my bad performance for this particular threshold. And then we'll try different thresholds and see if we can change the ratio of good versus bad. The idea is I want to find a cutoff or a threshold that maximizes my good performance and minimizes my bad performance. Okay, recall that our sensitivity was perfect. It's 100%. So that's this one over here. And then my false positive rate was actually pretty high, which is 0.87 or 83. I think it's 83. Okay, so that's where we would plot this performance for this threshold of, this is threshold of 0.15. Okay, and then we're going to try another threshold. This is threshold of 0.25. So we move down a bit, and now we have 2 true negatives. We still have these 4 false positives, and then these 4 are correct identifications. So now we can look at the sensitivity is still 100%. My specificity is going up a little bit. So my performance in terms of identifying true negatives is getting better. My false positive rate or 1 minus specificity is going down a bit. So now it's only 0.67, which is getting better. Okay, so just keep in mind it's 1 versus 0.67 for the threshold of 2.25. So this is 1 versus 0.67. And this is threshold of 0.25. This is threshold 0.15. Okay, now with 0.35, we get 3 correct negatives, and then 3 false positives, and then these 4 are still correct. So we still have 100% correct on the sensitivity side. Specificity keeps going down, so now we are at 3 versus 3, so 50%. Specificity has gone down at 50%. So this is 100%, and this is 50%, 0.5. This is the threshold at 0.35. This is 0.25, this is 0.15. And now with the threshold of 0.45, we have 4 correct negatives, 2 false positives, and 4 correct yeses. So that's the summary here. Again, sensitivity is still perfect. Specificity keeps going up to 0.67, and the false positive rate keeps going down, which is what we like to see. So remember, it's 1 versus 0.33 for the threshold of 0.45. So over here, 1 versus 0.33 for a threshold of 0.45. Okay. So we are still doing very well. So this is our good performance. It's still at 100%. Our bad performance keep going down, which is definitely moving in the right direction. Now with the threshold of 0.55, we have 5 correct no's, and then 1 false positives, and then these are all correct, so we're getting really, really good. Okay, so again, 100% sensitivity, specificity now is 0.83. Our false positive rate has dropped to 0.17. So 0.17 is over here, and this is still perfect at 1. And this is the threshold of 0.55 now. Okay. Now with 0.65, we get perfect classification. So these are all correct, and these are all correct. So it's 100% accurate. 100% accurate on this side, 100% accurate on this side, 0 false positive rate. This is as good as it can get. So this is our best model, as threshold 0.65. So 0.65 is our best threshold. That's here at 100% true positive rate and 0% false positive rate. You can't get any better than that. So this is the best threshold. And then if we keep moving the threshold up to 0.75, we start to have misclassification. So this is 1 error over here. And so my sensitivity starts to drop to less than perfect, right? So 70.75, my false positive rate remains 0. So this is why my next dot over here is 0.75. The true positive rate has dropped to, 0.75, and the threshold is 0.75. My false positive rate remains 0. At 0.85, we now have 2 false negatives. So the 2 false negatives over here is hurting my sensitivity rate. Now I'm down to 0.5. My false positive rate is still 0. So that's my 0.5 here. Okay, so this is the 0.5 false positive rate. The threshold is 0.85. Now with the threshold of 0.95, I'm going to make 3 mistakes over here. And those are the 3 mistakes over here that brings my sensitivity rate down to 0.25. So that's the 0.25 over here. The threshold is 0.95. This is 0.25 true positive rate. And that's it. We've gone through all possible thresholds. And these dots, you can actually connect them to produce the ROC curve. So the curve is really just connecting these dots. And every dot is basically a true positive versus false positive ratio for a threshold. Okay, so when you connect the dots, you want to find the spot that is in the upper left corner because that's usually our best performing model. That gives you the best true positive. So you want to maximize your true positive and you want to minimize your false positive. And that's why we're always looking for this corner. So usually in textbooks and lectures, you will see in your actual results, you will see ROC curve that looks like this. So what you want to do is you want to look for the upper left corner. That's usually your best model. So that's your best threshold, always in the upper left corner. AUC is area under the curve, so you can actually, most of the software will tell you exactly how big this area is. So the area is this area, and when you get perfect classification, which is what we saw in our example, you actually get this sort of square kind of curve, then you will get 100% area under the curve, and that would be a really, really good model. Okay, but if you get an ROC curve that's on the diagonal, that means no matter what you try, no matter what threshold you try, you get the same true positive rate as the false positive rate, meaning you're guessing. So 50 is just pure chance. No matter what you do, you're guessing. So this model does no better than chance. You might as well just flip a coin. Okay, so to select models, you can, for every model you have, you will get, each model will have its own AUC score. So basically when you're comparing models, you're comparing AUC scores, and basically you want to pick the model that has the biggest AUC because you're trying to maximize the area under the ROC curve. And that's all. Okay, so finally in R, I just want to remind everybody there's a very convenient library called ROCR that you can use to produce the ROC curve. In order to do that, you first of all have to build a prediction model using the predicted y hats versus the actual y. And once you build this prediction model, you can use that here, oops, missing a parenthesis, to build your ROC performance curve. Okay, so when you do that, you can actually specify how you want to construct the ROC curve. Now this is the X, this is the Y, so X is FPR, which means false positive rate. TPR is true positive rate. So that's basically how we constructed our ROC curve in the lecture. Okay, false positive versus true positive. However, if you look at the documentation for this library, you can see that there are lots of different parameters you can use. We've used the true positive rate and the false positive rate, but you can also construct ROC curves using other performance measures like accuracy, error, fall, out, recall, so on and so forth. There are many, many more. There's like another page of options. So many different performance measurements that you can use to construct alternative ROC curves. So you can do whatever you want. You just have to keep in mind what performance metrics you have chosen. You have to interpret your ROC curve accordingly. That is all on the ROC curve. Thank you very much.